right, so the idea of the derivative. So, if we look at page, the very bottom, page 25, it says a derivative is one of the two most important concepts in calculus. We'll devote much time and effort to derivatives. Various subtleties and puzzles will arise along the way, but the basic idea is simple. For a given function f, the derivative, so for a given function f, which you're going to see, we're going to think of as our amount, then the derivative, which we're going to denote with this notation right here, which we read that as f prime. That's what that little slash, or whatever you want to call it there above the f, that is f prime is what we say when we see that. Okay, f prime. Okay, so for a given function f, the derivative denoted by f prime tells us the rate of change. And now we're talking about instantaneous rate of change of f. The instantaneous rate of change of f. So, what do we mean by amount? Okay, so let's say f is miles. Okay, then the rate of change could be miles per hour. Could be miles per second, miles per minute, but it's a rate of change. So now if we're talking about the changing cost of these textbooks, then our f function might be dollars, and our f prime might be dollars per year. How much it's rising per year. Okay? It's a rate. Okay? Oftentimes in terms of time, but not always. Right? It could be dollars per book. Right? We might be, if we manufacture this many books, the price is changing at a rate of this many dollars per book. So it doesn't always have to be a rate in terms of time. Okay? Or a cost of an item changing could be the rate of change as you get bigger and bigger sizes, the cost per ounce goes down, right? So it could be the dollars per ounce or the dollars per pound or something like that, right? But the word per is going to be in there. It's a rate. It's a rate. So f prime is going to be a rate of change, okay? So f is more like an amount. Now you can have a rate of change of a rate, right? What if your f function was miles per hour? What's the rate of change of miles per hour? Miles per hour, which can be written miles per hour squared. That's acceleration, right? I don't like to use that, to be honest with you. I think miles per hour makes more sense, okay? But it's shortcutted to miles per hour squared, okay? But so the amount could be how fast you're going, miles per hour, and then the rate that's changing. If your velocity is changing, then its rate of change is the miles per hour, okay? So you can have a rate of change of a rate as well. So your amount function could be a rate, and then f prime would be the rate that rate was changing, okay? All right. So this section is going to be a lot about notation. We've already talked about this idea of rate of change, so it's going to be getting comfortable with this notation. All right. Notice on my goals over here for the day, it says we're going to gain an understanding of the derivative as a slope at a point and as instantaneous rate of change. Because we talked about both of those when we were doing those explorations, right? And they're going to see it here. So in the blue box on page 36, they say what we just said, that f prime is going to be the instantaneous rate of change. Now notice how I just wrote f there instead of writing f of x. And here it would be f prime of x. So, right, a lot of times you'll see it written that way. But a lot of times we don't care whether the input is x. That's all f of x does, is it tells us the input is x, or t, f of t, or f of whatever, right? So a lot of times when we talk about the function, we just say f or f prime, right? So you'll see that a lot in problems. Okay, it says we'll sometimes use derivative and rate function interchangeably to describe f prime, and when we do, we'll call f the original function or an amount function, and we'll revise and make this better later. Okay, so here we go. We've got this situation. We've got, here we go with Bismarck. All right, so on October 1st, 2000, a car enters Interstate Highway 94 from the state capital of Bismarck, North Dakota. For several hours, the car moves, sometimes east, sometimes west. So think about here on our own interstate on-ramp here. We could go east or we could go west on the interstate. T is going to be the elapsed time in hours since noon. P of T is going to be the position in miles on the interstate. And V of T is going to be the eastward, that's important now, eastward velocity. So why does that matter? Because it's direction and speed. So if my velocity is positive, what's that tell you? We're going east. Velocity is negative, we're going west, right? And that makes sense because on a map, we kind of want right to be positive, we want left to be negative, so we're going to make east to be positive, right? Typically north would be positive, south would be negative, okay? So it's the eastward velocity. Okay, so here we've got a graph, a couple of graphs of this vehicle moving along for an 8-hour time period. Okay, so let's look at and compare these two. Now, one of the things you're going to have to do on your homework is they're going to ask you some questions. They're going to describe a situation like this, and they're going to ask you some things, tell you to put it into words. So if I tell you that P of 2 is 100, okay, what does that mean? Okay, really good. I would clarify that just a little bit. What would be better than, say, 2 hours in? It's from noon. So at 2 p.m., the car is 100 miles east of Bismarck. Is it moving? Just based on the blue statement, is the car moving? What do you mean by no? It stopped? You don't know if it's moving, right? Okay, so that's a different answer than no, it's not. So is it moving? Could be. We don't know. We don't know. We just know that at 2 o'clock, and that's this point right here, okay, we just know at 2 o'clock that that car is 100 miles east of Bismarck. Could be coming back towards Bismarck, might be going away, might be stopped. Now, if we look at the graph, can we tell what it's doing? What's it doing? Since the graph is increasing, it's moving what direction? Further east, right? So, because it's getting farther and farther away from Bismarck, right? Remember, this is miles over here. So it's getting farther and farther away from Bismarck. Okay, now let's look at that point over here. That point over here is right there. V of 2 is about 70. Now what does that tell me? Your velocity at 2 p.m. is a positive 70 miles per hour. So what does that tell you? Just that alone. You're going in an eastward, because it's positive, you're going in an eastward direction at 70 miles per hour. Now, this alone, do we know if the car is east or west of Bismarck? No, we just know it's going in an eastward direction. Now, you put those two together, and then, yes, you know that the car is 100 miles east of Bismarck, and it's moving in an eastward direction at that velocity. Now, we could tell that because, again, this is positive. Now, here's my question to you. We talked about slope. What do you suppose the slope of that line is right there? Don't try to calculate it. The answer's there. What do you suppose the slope of that line is? The answer's on the screen in blue. No. 10%. No. Easier than that? No. 100 over 2. 70. Isn't it? isn't this the rate of change? This is the miles per hour, right? This is the rate of change at this point. This, and if you look down here at the second paragraph on page 37, V of 2 is the same thing as P prime of 2, right? Remember we said if the amount function is miles, the F prime, the derivative function, is miles per hour. It's the rate of change. Now, we've talked about his rate of change, but remember when we did the problem with the door swinging open? And we talked about the slope at that one point. We asked what's the rate of change at that one point. We picked 2 points really close together. Remember that? But now we can't do that here because we don't have an equation to plug it into, right? But we picked 2 points really close together and did the slope. Now what we will do, I saw some of you look at this, we will draw some tangent lines in here and we will estimate slope. We'll do a little rise over run and we'll estimate it. But we know that because of what we were just told here. Okay, so the V function could be rewritten as P prime. So this function here, I'm going to call that P of T, and I'm going to label this one P prime because it's related to the P graph. It is the rate of change of the P graph. Okay, so that's in the middle of page 37. It says V gives the instantaneous rate of change of position. In symbols, this means that V is equal to P prime. So this is the V function, but that is the same as the P prime function, the rate of change. Okay, so notice that P and V can both take on positive or negative values. So then they give you a couple more. Okay, so let's put these in red. So they say, notice that P of 6.5 is roughly negative 40. So right here at 6.5, now what time of day would 6.5 be? 6:30. So at 6:30, this car is doing what? Or is where? It's 40 miles west. So what, I mean, just looking at this graph, the car goes east for a while, then it comes back to the west, and what's happening right there? It's back to Bismarck, right? And then it keeps going to the west again, right? And then it turns around and comes back, just out for a drive, I guess, right? And then, what's that? Yeah. Right, yeah, who knows? I mean, they went, they picked something up, whatever. They're just driving around, okay? And so now they're back west of Bismarck. Now, what else do you notice about the graph right here at 6.5, the P graph? Is it at a minimum? I don't think it's quite at the minimum. That looks like that's a little past 6.5. I think it's a little bit before it. Over here, we got 6.5, and what does it say? It says it's about negative 60. I'm not sure I believe them, but they're saying that the V graph, which would be the P prime graph at 6.5, they're saying is about negative 60. Now, what's that tell you? It's going 60 miles per hour in the westward direction. And if you look at that, it looks like that's what it's doing, right? It's heading back to the west. Now, it's about to turn around, though, isn't it? Now, let's look at a couple of, let me make these black. Let's look at, speaking of a minimum maximum, let's look at that point right there. What does that correspond to over here? Isn't that right there? Okay, that's a huge deal for us right there. The max of this function is a root of this function. Now, doesn't that make sense? Let's think about slope. Now, I've already jumped ahead because at the top of page 39, it says the derivative, f prime, is the slope of the graph at that point. But we already knew that from what we did with instantaneous rate change. So it's instantaneous rate change, but it's slope at a point. What's the slope right here? If you drew a tangent line right there, it'd be flat, wouldn't it? The slope is 0. So what you notice here, hopefully what you notice, and then right here at this minimum, we're back to 0 right there, too, right? That's that turnaround spot. So hopefully some things that you notice here is that this graph over here, now I'm going to say this might be worth writing down. Let me go back. Well, let's write it on the board. F prime y values are the slopes of f. Right? if the function f prime is the slope or the instantaneous rate of change of the f graph, then what we're saying is the f prime graph is just a plotting of the slope, the instantaneous rate of change of the f graph. So if we look at this, so the slope here starts out what? Well, it's going up. This graph's going up. So the slopes are positive. So the slopes start out positive and pretty much the same. Are the slopes changing much right here? No. Look at this graph. See how it's at about 50 and staying at about 50 for a while? Does that make sense? But then they go up. Then this graph goes up. Well, that's because doesn't this seem to get a little steeper right through here? This gets a little steeper. So its slopes are going to get a little bigger. Now, what happens right about at 2? A little past 2. What do you got? Is that when it's about the steepest? Does that look like you about have an inflection point there? Kind of looks like it's curving up a little bit, then it starts curving down. Look what happens here. You got a peak over here. That's when the slopes get their steepest, which is right here. Now the slopes start getting less. Now it's still positive, right? This slope is still positive here, right? Right?
Yeah.
The graph's still going up. But it's not going up as much. Like the slope might be 20, 15, 10, 5. Does that make sense? So what do you got here? 20, 15, 10. Do you see why this is going down? Because it's not as much. Then all of a sudden you got a slope of 0. So now what do you notice here? This part of the graph, this blue part of the graph, when this graph's going up, corresponds to this part of this graph. Right? What do you notice? When this graph is going up, this graph is positive above the x-axis. Okay, you guys are going to get real used to that. When you look at a p prime graph, an f prime graph, when I talk about when is the function positive, we're talking about when is it above the x-axis compared to when is it below the x-axis. That's going to be a big deal. Now, in this graph, we don't really care about that so much. On this graph, when the position's positive, what's that tell you? No, not it's going east. It is east of Bismarck. When this one is positive, it is east of Bismarck. And when it's negative, it is west of Bismarck. When this graph is positive, it's going east. And when this graph is negative, going west, right? See those two? So it's good. I tell you what's going to happen is you're going to see over the course of next week is we're going to be comparing and looking at connections between the P graph and the P prime graph, the F and the F prime, and trying to keep those in our head, and it's going to get confusing. And we're going to work really hard at listing all those connections and organizing them so we can make sense of them. And then over time, we'll use them so much that they'll become almost automatic. But in the beginning, if you're feeling like it's a little much, it is. So hey, just stay with it. Okay? Now, when this graph's going down, which goes all the way to here, what is this graph? It's down here, all the way to there. Remember the two black dots. This dot and this dot corresponded to where this was 0, right? So this whole time, this thing has negative slopes, so this is going to have negative y values. Okay? All right. So there's a lot of stuff going on, so that's just a little bit of an introduction to that. Now remember, speed is different than velocity. Speed is the absolute value of velocity. Matter of fact, that's not a bad thing to write just right now. Speed equals the absolute value of velocity. So if we were going to talk about the speed, then we don't care about what direction. So that would be just taking, remember we talked about this the other day where you take the absolute value, you just flip up. Didn't we talk about that? You just take what's negative and flip it up to positive. So if you wanted the speed graph, you just take your velocity graph, take all the negatives and flip it up, right? And then that would just tell you how fast it's going, but not what direction. Okay, so there's a lot of stuff on page 37, and then of course we talked about acceleration a little bit. All right, so we talked about units. So it's always important to understand that, okay, so here you got, so if you got the P graph, here's miles, here's hours. Your derivative is always going to be the miles divided by the hours, because that's what slope does, right? Slope is the y's divided by the x's, rise over run. So whenever you have a P graph, if you want to know the units for P prime, you simply take the Y values divided by the X values. And then if we wanted to do the derivative of this graph, then it would be the miles per hour divided by hours, right? Which is what we said, that'd be acceleration, miles per hour per hour. Miles per hour per hour. Now that works out. If you do miles per hour divided by hours, well, if you divide by hours, that's the same as multiplying by 1 over hours, right? Dividing by hours is the same as multiplying by 1 over hours. Well, that's why you see it's miles per hour squared, right? That's why you get miles per hour squared when you do miles per hour, okay? They're the same thing, but I just think miles per hour is easier to understand. All right, so then we can talk about it as slope, so we can do that. Okay, now let's turn to page 40. So on page 40, it talks about slopes as tangent lines. Let me see if I have. No, I don't. Let me pull that up. Okay. Oops. Okay. So there's a nice graph here of tangent lines, and they do a nice job. When you think of a tangent line, when we talk about the slope of a graph, we're talking about the slope of this graph. We're thinking about slopes at points, right? That means the slope of the tangent line. So here's an example, and they give a nice example. They talk about, imagine a car driving along a curved highway, and think about the headlight, right? As where the headlight would be shining, right? So if I'm driving this way and I'm right here in the car, my headlights would be going like that. If I was coming this way, my headlights would be shining there. So if I want to do that tangent line, wherever I am on the graph, it goes like that. Okay, so when we talk about x cubed, that's one of the graphs that I talked about at one point. I can't remember if it was in this class, might have been the other class, but the graph of x cubed, now I always have a tough time drawing that exactly, but right there at the origin, it is flat. The tangent line, you might say, well, the tangent line shouldn't cross the graph. Well, sometimes it does. Like on x cubed, there isn't, right at this point, the slope is actually 0. But just at that one point, it's not like the x cubed graph goes flat for a ways and then goes up. It's always going up. The x cubed graph is always going up. Each point's a little higher than the one before it. But right there at that one spot, the slope is 0. If you were going to draw a tangent line there, okay, they're getting less. Think of your headlights. Right there at that point, it'd be horizontal. Then it goes back up like this, right? So there's that one point. We call that a flat spot. So we got local max right here. We got a local min right here. This would be what we call a flat spot, where the slope is 0. Okay? All right, so you're going to have some things with some notation questions you're going to have to be able to do. All right, let's go over to page 41. There's a couple of applications of this that we want to talk about. What time we get to be? Okay. So the first one, the first application, again, what we talk about a lot here is velocity and position, because that's just an easy rate that we all are familiar with. So we talk about rates of change, that's just an easy one to do. So we'll spend a lot of time with that one. But if you're just talking about an F graph in general, right? If I just say, what does F prime of 2 mean at this point? And forget speed and velocity and any of that. Just talk about a plain old F graph. And I ask you for F prime of 2. What would describe to me what that is? The instantaneous rate of change of the F graph at x equals 2. Or, Will's got one of them, the slope of the F graph at x equals 2, right? Now, if I'm talking about, let's think about those two. They're interchangeable. They mean the same thing. But in a speed problem, in a miles per hour problem, then I think rate of change is probably what you think of. If I'm just talking about an F graph, then I think it's slope, right? To me, if you're looking at a graph, you don't think about the rate of change of that graph, right? You probably think of the slope of that graph, right? So I think if you're looking at just some F graph that you don't know what it's about, okay, like this one we just had up here, this guy right here, this is just some F graph. If I talk about F prime of 2, I'm talking about, if I ask you to find F prime of 2, what I'm asking, you might have some of this today. I'm going to draw in this tangent line, and I'm going to say, okay, if I go over 1 it looks like I go up, oh geez, what is this, 5/10? So this looks like it might be about 8, and that might be 6 negative, right? So it looks to me like I went over 1 and up about 2. Would that be fair to say? So this to me looks like, so I would say on this graph that f prime of 2 is about 2, right? This is saying the slope of the f graph at 2. Make sense? Okay, and here'd be one way to get it. Draw in a tangent line and do that. Okay, and so we may do some of that. There might be some of that in your homework where you actually are going to sketch a line like that. All right, so anyway, here's on the middle of page 41. They've got a couple of equations here that you should write down. First one, h of t equals h sub 0. We kind of write this backwards from what we normally would, but than I normally would, but I'll just write it the way they do. Minus, I'm going to do the feet one because that's what we usually do. Okay, gravity is negative 9.8 meters per second squared, right? Acceleration of gravity. What is it in feet? Negative. Do we know that? It's negative 32 feet per second squared. Yeah, we know that, but I can just tell you that's the acceleration of gravity. Okay, this is an object, this is the height of an object in free fall. So if I go up to the roof and I drop a baseball, if I stand here, I go outside and I stand here and I throw up a baseball, right? Once it leaves my hand, it's in free fall, right? The only thing acting on it is gravity, okay? So h sub 0 would be the initial height that I drop or throw the thing from, the height when I release it, okay? V sub 0 here, so that's h sub 0. V sub 0 here is the initial velocity, okay? So if I throw it, so that'd be the velocity when it leaves my hand. If I just drop it, the initial velocity would be 0, okay? If I just drop it. And then t, of course, is the time that it's in the air. So t0 would just, if t is 0, of course, these two would just be disappear, and your height is your initial height. That's why h sub 0 is your initial height. Okay, so if t's a 1, that'd be after 1 second, let's say. If t's a 2, that'd be after 2 seconds, and so forth. Okay, and then the velocity equation, which would be h prime. Okay, this would be the velocity equation of the ball. The velocity of the ball at any time is simply v sub 0 minus 32t. And that's because what's happening is the ball's going to lose. That's what acceleration of 32 feet per second means. Negative is the ball's going to lose 32 feet per second in velocity every second. Okay, unless it's going down, it's going to gain in velocity because it's negative, right? So if the initial velocity is 0, then every second it's going to be going faster and faster. Negative 32, negative 64, negative, right? Because every second it gains 32 feet per second. It's going down. It's going up. It's being drugged by gravity. It's going to lose 32 feet per second every second, okay, of velocity. And so if I throw it up with a velocity of 100 feet per second when it leaves my hand, 1 second later it's going to lose 32 feet per second of that. And then another, and then another. All right, anyway, those are a couple of equations. There's a problem in the homework where they're going to ask you, and basically it's not really calculus, to be honest with you. It's just an example of a rate of change. So the question they ask you, just an algebra 2 kind of problem, it asks you to plug some numbers in. It's going to give you an initial velocity. It's going to give you an initial height. You're going to plug those in. You're going to have these equations. You can graph them if you want. You can use your calculators for sure. But so just for an example, if I ask you, so there's 2 equations. How high is the ball after 3 seconds? What are you going to do? Put a 3 in the top equation for t. Okay? How fast is the ball moving after 3 seconds? Put a 3 into the bottom equation. Now, those are the easy ones. The ones that are a little trickier is, when does a ball get to its highest point? Now, you could graph the top equation, right? Trace to its peak. But what we just learned, what happens at the peak? The slope is 0. Isn't this equation the slope? This is the velocity. But don't plug in a 0. Or plug in a 0 where? Jesse, you said plug in a 0. For the v, right? Plug a 0. In other words, set the velocity equation equal to 0, right? Because what does it have to do when it gets to the peak? You said slope is 0, I agree. But what's the velocity when it gets to the peak? It stops. It goes up, stops, comes back down. So you're asking when the velocity is 0. So you want to know when's the greatest height, you actually use the velocity equation. Set it equal to 0. Solve it. Okay? When does the ball hit the ground? No. Well, that's not going to work because it's not going to. The equation's going to think the ball can go right through the ground and keep going. So what else is going to be 0 when the ball hits the ground? The height is going to be 0. So you want to put a 0 on this side, right? Put a 0 on this side and solve this. That'll tell you when it hits the ground because its height is 0, right? Its height is 0. So you're just going to have these equations. They're going to ask you questions about them, and then you're just going to answer them by doing what we just did right there. Okay. All right. So that's one example of something that uses velocities and stuff like that. Okay. And then the famous page 42 speed limit law. The speed limit law. Now this will come up all throughout the year. All throughout the year we will have problems and we'll be working along and we'll be stuck and, or maybe not, but we'll read the problem and it'll be like, oh, what's this problem talking about? And hopefully you'll all go, oh, this is speed limit law. Hopefully. All right, so the speed limit law, we're going to write this out. I wouldn't mind if you wrote this out in your notes. I'm going to write it here, okay? So it says, let F be defined for all x in the closed interval AB. So that just means it's not undefined anywhere, right? It's not, there's no holes, there's no breaks, there's nothing weird going on, right? It's defined for all x in the closed interval AB. And let M be any real number. That's just kind of setting the stage, right? That stuff there. Okay, here's the real nuts and bolts of this. If f prime of x is less than or equal to m for all x in AB, then, underline that in red, f of b minus f of a is less than or equal to m times b minus a. Now, I know what you're saying. I know you're saying, obviously, everybody knows that. But that's not what you're saying. Really? Okay, well, let's break it down a little bit then. Okay, so f prime, when we hear f prime, we think what? Rate of change or slope. Very good. We hear f prime, we think rate of change or slope. Right? In this case, let's do rate of change first. We're going to do it both ways. We're going to talk, because it's talking about speed limit, so let's talk about rate of change. So let's use miles per hour as our example. Okay, so f prime is miles per hour. So this is like saying if miles per hour is always less than or equal to m. Now I don't know if you want to write this in here right now. Maybe it's up to you. But I'm just kind of jotting here. If miles per hour is less than or equal to m all the time, x would be like time, right? And this is maybe from 0 to 8 hours, right? For 8 hours, if our miles per hour is always less than or equal to m, what can we call m? Huh? Well, yeah, but I mean, in terms of miles per hour, what can we call m? If I tell you that my miles per hour, for those 8 hours I drove, my miles per hour were always less than or equal to 80. What is 80 then? What's miles per hour, but more than that? Well, okay, could be the speed limit, but okay, well, but speed limit's not 80 anywhere, right? If I say for 8 hours I drove and my miles per hour were always less than or equal to 80. Yeah, it's velocity, but more than that. So for my trip, yes, 80 is my max, right? My max velocity. Wouldn't that make sense? Why do you think we use the capital M here, right? Okay, so, because what I'm trying to do is to make sense of what this is saying, right? So let's call M my max velocity. That's what M's going to be. M is my max velocity. That's what this statement is saying. If my rate of change is always less than or equal to m, then m is my max rate of change. Okay, now what's F going to be? If F prime is miles per hour, what's F? Miles. And what would be the miles at B? What's B?
8 hours.
I said 0 to 8 was my trip, right? So what's B? What part of my trip is B? The end of my trip. So this would be the miles at the end. So I was 500 miles away. And then what's the miles at A? Where I started, right? So let's say I started 200 miles away. And I ended 500 miles away. So what's F of B minus F of A? The distance of my trip. So this is my distance traveled, right? So this is my distance traveled, right? My distance traveled has to be less than or equal to my max speed. Didn't we say M was my max speed? Times, what's B minus A? That's the time of the trip, right? That'd be 8 minus 0, right? So this would be the time of the trip. Oh, well, isn't that distance equals rate times time? Isn't that all that is? This is saying that, okay, if I know my max speed is, so now we've got 80 as our max speed and my trip is 8 hours long. So if my max speed is 80 and I know I traveled for 8 hours, then isn't it true that my distance traveled has to be less than or equal to 80 times 8? 80 times 8, right? I know I went for 8 hours, and I know the most I ever went was 80 miles an hour. Then the farthest I could have went was 640, right? Does that make sense? So, if you say, yeah, big deal. That's obvious. That's this thing right there. Here's what's big about it. This says that if you know something about your speed, then you know something about how far you went. Okay? Would you agree with that? If you know something about your speed, maybe it's changing, but what do we know? We know the most it ever was, right? If you know something about your speed, then you know something about how far you went. Okay, but now let's put that down. Again, big deal. Well, now let's put it in terms of derivative. This is what this is saying is, if you know something about f prime, you know something about f. And that's the real importance here of the speed limit laws you'll see. Now, in blue, let's talk about slope now. Let's put this in terms of slope. So now, f prime, let's don't think miles per hour, let's think slope. So now, if I've got a graph f, and I tell you that the slope is always less than or equal to 3, what's that tell you about that graph? What's that 3 mean? Slope measures what on a graph? Right for the peep. If the slope is 3, it tells you what about the graph? How steep it is. How steep it is, right? How steep it is, right? Graph 4 is steeper. Graph of 5 is steeper yet. Graph 6 is steeper yet, right? So what this tells me is the steepest the graph would ever be is 3. Okay? So M could be my max what in this case? Slope, right? Or you could say steepness, right? It helps you picture. But that's the max steepness. That's the max slope. Okay? It tells you the steepest it's ever going to be. Okay? So I'm telling you my slope is always going to be less than or equal to 3 on this graph. Okay? And we're going to go from 0 to 8 again. Right? We'll go to 0 to 8 again. So now what's f of b? That's the y value of the endpoint, right? So this is the y value at the end. And what's f of a? The y value at the start. A is the start, B is the end, right? So this is the y value at the end minus the y value at the beginning. What does that tell you when you subtract those?
12.
What's slope? Algebra 1, when you calculate slope like this, what would you do? Rise over run. What is f of b minus f of a? Isn't that the rise? It's a difference in the y's. Isn't that the rise? That's how much the graph went up. Now, it might have went down, right? It could have went down if slope's negative, right? Could have went down, but let's just say, to make it easy, let's say it goes up. Isn't that the rise? Here it was distance traveled, but this is the difference between your y value at the end, your y value at the beginning. This is your rise. This is your rise. This is how much the graph went up from beginning to end. Okay? Is less than or equal to, now remember, m was my max slope. M was my max slope. Times, it's what's b minus a. Come on. Come on. Don't make, what? The run. The run, right? B minus a, B minus a, B minus a would be the run, right? F of b minus f of a is the rise. B minus a is the run. Okay, so, doesn't this say, if I tell you that my graph always has a slope that's 3 or less, that if I go over 8 times 3, what's that? 24. If you know the slope is always 3 or less, if you go over 8, what's the most you could go up? 24, right? Because it'd be 24 divided by 8, 3, right? So the rise has to be less than or equal to your biggest slope times your run, right? So your biggest slope, 3, times your run, 24, that's the most it could have went up. Okay, it's the same exact idea. On the one hand, we're saying the fastest the graph changes times how long it's changing gives you the most it could go up. This says if you know how fast your speed is times the length of your trip, which again is like the run, then that gives you, then this would be the farthest you could travel. So the y is like how far we're traveling, right? So they're interchangeable. Instantaneous rate of change or slope. This is a speed limit law. So what's a problem look like that? A real simple problem would look like this. Let me just do a real simple one for you, and then we'll let you get started here. But so if I told you that f prime of x is less than or equal to 2, and I told you f of 3 is equal to 10, could f of 6 equal 20? Could it? Everybody's looking down. You said, yeah, well, why?
I thought you just times the 2.
And don't think of the speed limit law as a formula. Don't think of the speed limit law as a formula. Think of the speed limit law as an idea. The speed limit law says if you know how fast you're going and you know how long you're going for, then you should be able to figure out how far you could have traveled. Right? Do we know how fast we're going? 2, do we know how far we're going? Our run is from where to where? No. No, it's not. 10 and 20 are y values. 10 and 20 are y values. The x values is your run. We're going from 3 to 6. So how long are we going for? We're going for 3. Okay, you want to use miles per hour? Let's go miles per hour. So we're going for 3 hours, and how fast are we going? Where's our speed up there? F prime. So we're going for 3 hours, and we're going 2 miles an hour. So how far can we go? We're going 3 miles an hour, or excuse me, we're going for 3 hours and we're going 2 miles an hour. We can go 6 miles. So how far can we go? Where do we start? 10. So what's the farthest we can go? To 16. Could f of 6 be 20? No. Now let's do it in terms of slope. I want you to get to the point where you drew this problem this way. You say, okay, I'm going to draw an f graph. F of 3 equals 10. 1, 2, 3. Here is 5, here is 10, and here I am at the point 3, 10. Now, they want to know 4, 5, and 6. Where could I be? Now, the most I can go up, the most my slope is 2, right? The most my slope is 2. So that means if I go over to 6, I just went over 3. If my max slope is 2, what's the most I can go up? This is how you would justify this problem. You wouldn't try to fill in the formula on the speed limit law. You would do a little picture here, and then you would write some words. And you would say, okay, if the most I can go up is 2, and I start here, then the highest I can be at 6. The most f of 6 could be is 16. So f of 6 could not be 20. Could f of 6 be 3? Could I have been down here? Does it say you have a positive slope? What's it say about the slope? Less than or equal to 2. So could it be negative? Is it negative less than or equal to 2? So could f of 6 be 3? For sure. The most this slope is 2. So if I go over 3, the most I can go up is 6, but I could have been anywhere else down here. Right? Anywhere else down here. Right? Because it says the slope's less than or equal to 2. So it could be negative.
Will we ever have like a negative?
Sure. Sure.
And a positive?
Oh, like an in-between. Like you can have an in-between, negative 2 and 2. Sure. You bet. I could give you that. Yeah. So you know the slope's always between negative 2 and 2. So now it could go over 3 and go up 6, or it could go down 6, and then that'd be the most. Right? And then so then you'd know the f values have to be in between that. So that's how I would do a speed limit law always, is I would plot the points, and I would take rise over run. You say, okay, you want me to go from 3 to 6? That's a run of 3. You're telling me the most my slope is 2, so if I go over 3, most I can go up is 6. Or if that was negative 2, go down. Right? Or something like that. Okay, that's the speed limit law. If they tell you something about the slope, and then you can figure out something about how far the graph went, that's basically the speed limit law. If you know something about how fast you went, it tells you something about how far you went. That's basically it. Okay, homework is the 1.4 questions. You can start on that. That is for Monday. Don't forget about that reaction article on Google Classroom. Read that article and write that little reaction. So you've got to have that done at 8:05. That has to be handed in, the turn button clicked on the Google Doc at 8:05 Monday morning. And then of course, the 1.4 homework questions. Okay? It's a lot of notation stuff, this F prime, and just a lot of different kind of questions. So I'll be here bright and early Monday morning if you need help. The IXL, those two IXLs, don't forget about those, C7 and C16. I'll give you a little extra time. If you've got those done by Monday, I'll count that for you. C7, C16 to 90 on both of those.